Good morning, everyone. In this video, I will discuss about the variation of acceleration due to gravity due to latitude. So, what is latitude? So, if you look at the Earth, let's say, for example, this is the Earth, and these two are the points that are on the opposite sides of equator. If we connect them, it will pass through the center of the Earth. So that we call as an x-axis. And this line here connecting the two poles, so that's y-axis. Any point on the Earth makes an angle theta with respect to this axis. So this angle we call as a latitude. So in simple words, latitude tells you the south-north or north-south position of the object. So for example, at this point P, theta is equal to 0. That means you are on the equator. And at this point P, your theta is equal to 90 degree. So this tells you that you are at the North Pole. Here, at this point, theta would be equal to negative 90 degree. That means you are on the South Pole. So in summary, latitude tells you the position of the object. Okay, so what is the goal of this video? The goal of this video is to derive an equation which tells you the variation of acceleration due to gravity due to the latitude. So let me talk you briefly here. First I will tell you overall idea that why does this g, acceleration due to gravity, depends upon the latitude. So all of us know that the Earth spins about its own axis. So and because of its spin, we have the days and night. And let's call that angular speed is omega. And the Earth spins about its axis, about this y axis here. Okay. So now, as the Earth is spinning about its axis, each point on the Earth moves in a different circle. For example, the point P here moves in the circle here. The point on the equator moves in the largest possible circle. Here at this point it moves in this circle here. So each point moves in a different circle. And if an object is moving in a circle, then there must be, and if you look at, especially if you look at it in a non-inertial frame, then there must be a centrifugal force. So in addition to the force due to the gravity, there is now an additional centrifugal force. So if the point P starts moving into a circle, then there are two forces acting onto the object. So the first force will be the weight mg, which is acceleration due to gravity, or that's the gravitational force, and then there must be a centrifugal force Fc. And because of this additional force, the net force does change. The net force will be slightly affected, and that's what we're going to study. In fact, we're going to derive the equation. And now, why would it change depending upon the location? So the formula for the centrifugal force is m omega square r cosine theta. Here r cosine theta is the radius in which the point P moves. And if you look at each point here, each point moves in a different circle. The larger the circle is, the greater will be the centrifugal force. So you can clearly see that centrifugal force will be higher at the equator and very lower, almost zero, at the pole. So there is a continuous change of centrifugal force or in fact increasing from the equator to the pole. So as the centrifugal force is changing, the effective gravity, or the apparent weight we can call, or the apparent acceleration due to gravity would change. And what is the exact equation? That's what we're going to do in today's video. So this video could be a little longer because it does involve a lot of math. So let's get started. So let us consider the Earth is spinning about its north-south axis with an angular speed omega, and we have point P which makes an angle theta with respect to this x-axis, or we call this angle theta as a latitude. So now if I look at this point here, and this point P is moving into a circle because the Earth is spinning about its axis. So if I look at this circle here, I can find out the radius of this circle. And how do I find out? So let's take a look into this triangle here. This angle is theta, so this angle must be theta. So this value, or this radius, would be r cosine theta. Or what you can do, you can draw a triangle So let's call this angle is theta, this is r, and if I have to look at the cosine, what would be the value of cosine? Cosine is the base divided by the hypotenuse, which is r. So base, which is this b, or that is in fact the radius of the circle, would be r cosine theta. So this is how we get the radius of the circle here. So let me clear this one. Okay, so once we find out the radius of the circle, the next thing is going to find out the forces acting onto this point P. So let's draw all the forces acting onto this point P. So one force we know for sure is the centrifugal force. So let's start with the force due to the gravity, which in fact acts this way here towards the center. So this is the force due to the gravity. And what's the value? Let's call this is my origin. The value is weight equals to mg. Is there any force? Yes, because the Earth is spinning about its axis, there is another force, and this force we call as a centrifugal force. The centrifugal force. Centrifugal force. So now we have the two forces acting onto this object P, and as a result the net force, or your net weight, or the net acceleration due to gravity on the Earth's surface is slightly changed, slightly different, and that's what we're going to calculate. So what's the strategy? How are you going to find out? So we're going to resolve this force into two components. The one component will be here, this component, and we have said this angle is theta, and we have another component. This component will be this way. So this angle is theta, so this angle must be theta. This component, as this angle is theta, and if I look into again this triangle, this component will be cosine theta. So let me write down here, this component will be cosine component, which will be equal to mg cosine theta. Why mg cosine theta? Because this force, or this weight, is mg, and if I look into this triangle, this component is simply cosine component. And exactly the same way, this component would be mg sine theta. Mg sine theta. That's all you need to know. So we do not need this force now. Okay. So now we have three forces. One force mg cosine theta along negative x-axis. There is a centrifugal force, and there is one force along y-axis, which is mg sine theta. The next thing is, what is the equation for the centrifugal force? I will write it down here. The formula for the centrifugal force is m omega square r, and this r is the radius of the circle in which this point P moves. So this would be the circle. And what is the radius? We already have calculated. This radius would be m omega square r cosine theta. You see, we already calculated that this point P moves in this circle, whose radius would be r cosine theta. So we have written down all the important information we needed, and the rest is simply the math. So again, the weight is mg, which is towards the center of the earth, and the centrifugal force, which is at this point away, radially away from this circle here. Okay, so what is the total force? If I look at this x-axis here, what is the total force acting along this axis? So the total force along x-axis would be, so this force minus this force, because these two are acting in opposite direction. So let it write down here. The total force along x-axis is mg cosine theta minus centrifugal force. So mg cosine theta, and what is the centrifugal force? M omega square cosine theta. Okay. And now what is the total force along y-axis? So along y-axis, the force is only one force, which is mg sine theta. That's what I have written down, mg sine theta. The life becomes so much easier once we have understood this portion. Now let me redraw these things now. So this is the total force, Fx, and this is the total force along y-axis. And these two forces now are mutually perpendicular, so I can find out the net force, and the net force would be in this way. So how do you find out the net force? So you can draw a rectangle using these two sides. So I have this force and this force, so I can clearly draw a rectangle, and the diagonal would be the net force. And this net force, considering the rotation of the earth about its own axis, gives the apparent weight. Apparent weight, if you consider the force, and if you simply consider the acceleration, it would give you the apparent acceleration. That is in fact the true acceleration. All right. So that's what we're going to find out, the magnitude of this acceleration or magnitude of this weight, considering the spinning of the earth. So now these two forces, Fx and Fy, are mutually perpendicular, and this is the apparent force or the net force, and the magnitude would be simply given by Fx square plus Fy square. So if I look into this triangle, this is Fy, and this would be my Fx, because these two are parallel. So this would be by Pythagorean theorem, it would be equal to Fx square plus Fy square, just in this right angle triangle. So my apparent force is Fx square plus Fy square, or the apparent weight. And all I'm doing is simply plugging in the value of Fx and Fy, and the rest is the math. So simply follow this one. It's quite straightforward, nothing complicated. But I will go over it quickly. So I have simply plugged in all the values, and you see on each side there is m, so I have cancelled out m, a little bit easier. Now this is a and this is b, so a minus b square would be a square minus 2ab plus b square. So if you expand, what you got, g square cosine square theta, 2ab terms plus b square and g square sine square theta. So I'm combining these two terms together. So I'll have this term and the rest as it is. Cosine square theta plus sine square theta, this is equal to 1. Remember, cosine square theta plus sine square theta, that is equal to 1. All right, so I have this equation. This is still a long equation. Now we're going to make this equation a little bit more shorter. So if you look at the value of omega, the omega is 2 pi over t. What t is? The t is the time period. What does that mean? That means how long does it take for the earth to complete one complete cycle? That's the day-night cycle. That's the 24 hours. So if you plug in the 24 hours and calculate, this is the value you will get. That is called the angular speed of the earth. Okay. So now omega is very tiny, 10 to the negative 5. So that means if you take the value of omega 4, you will get a very, very tiny number. So just do math yourself. 7.3 times 10 to the negative 4. And if you take the power 4, you will get something on the order of negative 20, which is extremely, extremely, extremely small. So if that is so small, or this term omega 4 will be very, very, very close to 0, almost 0. So we can simply ignore these terms. Okay, so now if we ignore this term, because this term is very, very insignificant, I'm simply keeping these two numbers. That's what we have. And now one more, I'm simply taking the g out here and simplifying, and this is a square root, which means it is the same as saying it is the power 1/2. Now I can binomially expand these terms. So for those who do not understand the binomial expansion, please take a look the binomial expansion. So if I do the binomial expansion, and if we ignore the higher order terms, what I will get, I will have this term times this power here, 1/2, and this 2 here, the 2 cancel, and I will have only this term here. Omega square r cosine square theta plus z. There will be other terms too, but again, because other terms will involve omega 4 and higher order terms, we can simply ignore those terms because those terms will be very, very small. So simplifying further, this will be the final equation of the acceleration, apparent acceleration due to gravity. So let me explain each term here. This term is the acceleration due to gravity. So when I say acceleration due to gravity, considering the mass and the radius of the earth. And this one is the centrifugal acceleration. This is the centrifugal acceleration. And this g prime we call as an apparent acceleration. That's how much acceleration appears on the Earth's surface. Or in fact, this g prime you can also call combines the acceleration due to gravity plus the spinning of the Earth and at the different latitude. Okay. So now once you know the acceleration due to gravity, the apparent weight would be simply given by mg prime. So if you know the g and if you multiply by the mass, that gives you the acceleration, the weight. So this is the weight, and this will be the apparent weight, and this would be the weight due to the gravity, and this would be the centrifugal force. So this would be the centrifugal force. Okay. So now, once we have this equation, we can now find out the direction of the apparent weight. So if you look at this equation here, or I have a picture here. Okay, so the next thing we're going to find out the direction of the apparent weight. So if you are on the earth surface, the earth attracts you towards the center of the earth. That is the acceleration, that is the acceleration due to the gravity. That's only taking the gravity into account. But if you also take into account the centrifugal force or the spinning of the earth, your weight would be slightly deviated from this acceleration due to gravity, and let's call that angle is alpha. So we call this angle as an alpha, and we're going to find out this angle alpha here. And in fact, the theta and alpha, if you calculate, will be very, very, very close. So, or in other words, there is not much difference between this theta and alpha, and I'm going to show you later in the video. So how do I find out the alpha here? So remember, the theta is the latitude, and this alpha is the direction of the apparent weight or apparent acceleration. So how do you going to find out this alpha here? So if you look again in this triangle here, this is my fx and this is my fy. So that this if I take the tangent of alpha, it will be the y component fy divided by fx, or rise over run. So fy divided by fx, which is mg sin theta, divided by this term here, m cancels out. So this is the tangent alpha. This gives you the direction of the apparent weight, and which does not depend upon the mass. And the same thing here, the acceleration due to gravity does not depend upon the mass of so that means for each object the apparent weight, and in fact the acceleration due to gravity, would be independent of the mass. All right, so this is how we calculated the apparent acceleration due to gravity, and we also calculate the apparent weight. So this is it from this video. If you have any questions, any comments, write down in the comment section below, and do not forget to like, share and subscribe the channel. Thank you very much.